You can write down a chess game as a sequence of moves in algebraic notation. But this format leaves implicit the main visual element of chess, that is, the position of the pieces on the board. When we play chess or talk about chess, we basically always want to see the position. We might furthermore overlay analysis on it, or fast forward through its evolution to show a quick overview of what happened in the game. Oh! You can write a proof in the Lean Theorem Prover as a sequence of tactic steps, but this format leaves implicit the main visual element of formal theorem proving, that is, the goal state. As we work on a proof, the goal state is always there, showing us what still needs to be done. Like with chess positions, we might overlay analysis on goal states, or fast forward to the end to get a quick overview of what happened. However, this default way of displaying goal states includes a lot of distracting clutter, and is not really ideal for telling the story of a proof. So my question today is, can we invent a better way to visualize formal proofs? Here's the plan. Given any proof, we will automatically extract its goal state data, and then we will use that to render an informative animation. The two main tools we will use are Infotrees and Blender. Theorem proving is a single-player game where the objective is to clear a set of goals. Each goal contains a logical expression you need to show to be true, plus a list of hypotheses that you are allowed to use. The way that you make progress is by applying tactics. A tactic might transform a goal, it might split a goal, or it might clear a goal. Tactics can appear nested within other tactics, and in general can have arbitrarily complex structure. Lean the language is expressive enough that goals can represent essentially any mathematical statement. Moreover, its syntax is customizable enough that it can directly embed two-dimensional puzzles, like this maze game, where you're trying to prove that the @ character can escape, or this chess puzzle, where you're trying to find a forced checkmate. A good first step toward animating these proofs is to understand how code editors display goals. When you open a Lean file in Emacs or VS Code or whatever, a background server process gets launched and starts listening for events via the language server protocol. On every change you make to the file, the server gets notified and recompiles the relevant code. It then sends updated diagnostic information back to the editor. Every time you move the cursor to a new location, the editor asks the server for the latest goal information at that location. In this case, however, recompilation is not needed because the server uses a data structure cached from the most recent compilation. Infotree is the name of that data structure, and it certainly contains a lot of information. For every piece of syntax in your source code, the Infotree remembers context about how it was elaborated. For tactics, this context includes the goal state before and after tactic execution, which is exactly what we'll need to make animations. Let's imagine what we want our final output to look like. We'll display the current goal state, the tactic that gets applied to it, and then its transition into the next goal state, and repeat. This is, of course, just a sequencing and rearrangement of the way code editors display the same information. But note that all of the distractions have been removed. Moreover, there's a new element we intend to add: smooth transitions, illustrating how one goal state morphs into another. There are many different software systems we could use to draw these animations. I chose Blender, largely because it was something I wanted to learn more about. In Blender, we create a separate text object for each character, and then we arrange keyframes to animate them. To automate construction of the scene, we use Python scripting, which Blender has good support for. Our main script accepts as input a JSON description of goal transformations, and produces as output a complete proof animation. Now we just need to compile the Infotree into this JSON structure. We will proceed in baby steps, defining a series of intermediate representations. First, we prune the tree, dropping unneeded information, such as the results of macro expansions. Next, we flatten the tree, pulling out any nested tactics. Then we compute string matching between goals of successive steps, using a simple greedy algorithm with a few heuristics. The last step is to export the result as JSON, using Lean's toJSON type class. And now we are finally ready to animate some proofs. Suppose A, B, and C are propositions. Given that A equals B is true, and that C is true, we want to show that A implies B and C. First we apply the intro tactic, which moves A into a new hypothesis, HA. Then we apply the constructor tactic, which splits the conjunction into two cases. In the first case, we apply the RWA tactic, which implicitly uses the hypothesis HA. In the second case, we directly use HC, the hypothesis that C is true. And then we're done. The Natural Number Game is a tutorial website that I highly recommend for lean beginners. Let's animate one of its proofs. This one starts with an induction, and then does a bunch of algebraic rewrites. Our greedy string matching algorithm does a pretty good job here. I think the way the symbols move in these goal transitions mostly makes sense, even in these somewhat larger, more gnarly expressions. After we apply the induction hypothesis HT, there are just a few more rewrites, as we work toward a trivial equality that can be discharged with the ruffle tactic. On a different problem from the natural number game, our greedy string matching algorithm makes some less optimal choices. Here we are about to distribute the multiplication on the left-hand side. If I were animating this by hand, I would choose to match up the subterms in a very specific way to emphasize how distributivity works. The greedy algorithm chooses a different way because it likes making longer matches. The result is a somewhat obfuscated animation. Minimizing this kind of suboptimal matching is a possible avenue for future work. Perhaps better heuristics would suffice, or maybe we could provide an annotation system. Tactics can apply to more than one goal at a time, for example via the pointy semicolon combinator. In such situations, we animate all of the corresponding goal transitions simultaneously. To finish this particular proof, we unpack the divides notation. We note that GCD AB divides both B and A, and then we combine all the quotients in a clever way to get exactly what we need. In the other branch of the proof, we note that GCD AC divides both C and A, and we again combine the quotients in a clever way to get what we need. We can, of course, also animate chess puzzles, like this mate in 5. And I just find it very satisfying to watch the Unicode pieces slide across the Unicode squares, governed by the same machinery that we've been using for more traditional mathematics. The king escapes to g3, but after a rook delivers a check on g2, and a pawn advances to g5, it's checkmate. I recently showed someone this animation of a maze game playthrough, and they pointed out that if you didn't know all the context about theorem proving and lean syntax and 3D rendering, you might dismiss it as a rather uninteresting demonstration. I laughed, and then set out to make a video that would painstakingly explain the context. And now it's time for one last proof animation, this one from the 2011 International Mathematical Olympiad. We are given a function f constrained by an inequality hf, and we need to prove that f of x is 0 for all non-positive x. We start with a reparameterization of hf, which is shown to be valid by a direct calculation. We then propose to show that for all negative x, f of x is non-negative. That follows from the n-linearith tactic, along with two particular instantiations of hf. Next, we propose to show that f is actually non-positive for all x. For the sake of contradiction, we suppose f of x is positive. Then we can choose t such that the right-hand side of hf is arbitrarily small, in particular negative. But that contradicts the other hypothesis f of neg. The rest of this branch just works through the details of that argument, ending with a calculation that relies on linearith. So now we know that for negative x, f of x is both non-negative and non-positive. Combining those facts yields that f of x is actually 0 for negative x. That leaves us with one last case to handle, when x is 0. Here we just need to choose the right arguments to plug into hf. It turns out -1, -1 does it. End of proof, end of video.